Now, welcome back, and we're moving right along into our new topic, which is waves, sound, and light. So we're going to start with waves. Types of waves. A pulse is a single disturbance that propagates from one point to a next. Waves can be classified as being either transverse or longitudinal. A transverse wave has vibrations which are perpendicular to its direction of propagation. Okay? And a longitudinal wave is one which has vibrations parallel to its direction of propagation, as you can see by the arrows in both pictures. Right? So this one is going, the wave is going up and down, and this one is going from side to side. A wave produced in a rope or slinky lying on a horizontal surface and vibrated from one end perpendicularly to its length is an example of transverse waves. The wave produced in water by an object vibrated perpendicularly into and out of its surface is another example of transverse waves. An electromagnetic wave, for example light, is also another example of transverse waves. Longitudinal waves are characterized by regions of high pressure known as compressions and regions of low pressure known as rarefactions. So here we have the examples of the compressions where we have a higher concentration of particles or matter, and the rarefactions, in here we have a lower concentration of matter. Matter could be molecules, atoms, ions. It's just, you could think of it as air. A sound wave produced in a solid, liquid, or gas is an example of a longitudinal wave. Now here we have it, and this is the comparison of a longitudinal wave to that of a transverse wave. This is a sound wave right here, and where there is a compression, it's synonymous to a crest, and where there is a refraction, it's synonymous to a trough. The wave produced in a slinky lying straight on a horizontal surface and vibrated parallel to its length from one end to another is also an example of a longitudinal wave. So all of these are examples of longitudinal waves. Waves may be classified as either being progressive or stationary. Progressive waves are those that transfer energy from one point to the next. Stationary waves do not transfer energy. Now here we have some wave parameters, or things associated with a wave. The amplitude, the wavelength, period, frequency, speed, wavefront, and phase. These are all things that we're going to discuss now that are associated with a wave. Let us go right on into amplitude. Amplitudinal wave is the maximum displacement of the vibration or oscillation from its mean position. So the amplitude is basically from the equilibrium point up to the top of a crest, or from the equilibrium point down to the bottom of a trough. That's an amplitude. So the height of the bump or the depth of the trough, right? If the amplitude of a light increases, the light becomes brighter. If the amplitude of a sound wave increases, the sound becomes louder. Now we're going to look into wavelength. Wavelength is represented by the Greek letter lambda. It is the distance between successive points in phase in a wave. For example, between two successive crests or two successive troughs. Okay? So that's the easiest way to describe it. Oh, it's not plugged in. The wave period is the time it takes for one complete vibration to occur. For example, the time it takes two successive crests, two successive troughs, or a successive crest and trough to pass. T is equal to 1 over F. That is where T must be in seconds, S or F to be in hertz, right? So T is actually period. That's the letter you use for period or the time. So again, the wave period is the time it takes for one complete vibration to occur. For example, the time it takes 2 successive crests or 2 successive troughs or a successive crest and a trough to pass. In the figure below, the period is 200 milliseconds, which is also equal to 0.2 seconds, simply because a milli is equal to 10 to the negative 3, so we just multiply 200 by 10 to the negative 3. Now, it says right here you have the crest and you have the trough, so that is why we say that this is a period. So it has to be a successive crest and a trough. Okay, so that's one period right there. So now we're going to go into frequency. Frequency utilizes the symbol F, or italicized F. The wave frequency is the number of complete vibrations per second. The frequency of a wave is also the number of crests passing a chosen point per second. So to calculate frequency, use the same equation we use for period and just transpose. So frequency is equal to 1 over period or time. So here we have frequency. High frequency, I have a lot more bumps in the same amount of time. So this is 1 second being represented here. So you have 1, 2, 3, 4 bumps, and then maybe a second here you only have 2 bumps. So this is low frequency. So less amount of waves being produced in the same time. And if you look at this, you will see that in the electromagnetic spectrum that I have here, you will see that gamma has a very high frequency, whereas coming right down to radio waves, you have a very low frequency. Okay? Looking at the picture below, a successive crest and a successive trough, which is a complete vibration, pass in a time of 200 milliseconds. 200 milliseconds, which is equivalent to 0.2 seconds, is the wave's period, T, or the time it took for the wave to pass or vibrate. To determine the wave's frequency, the following equation will be used. So remember, the frequency is how many waves would pass in 1 second. So that's why we have the 1 there. So we know that in 0.2 seconds we had 1 wave. So we want to know how much waves would pass in 1 second. And you just simply transpose. You could use this, you could use this. So you would say 1 second times 1 over 0.2 seconds. And see, it's the same thing. You're going to end up with 5 hertz. Okay? So you're going to end up with 5 hertz. Good. And that's what we get. Now the frequency of a light wave determines its color. Right? So whereas amplitude determines the amount of times waves will pass for a wave, or it would also determine, amplitude determines the intensity of the light, and amplitude also determines the intensity of sound. So amplitude deals with intensity, and frequency on the other hand deals with the color of light produced at the same time. So red has the lowest frequency and violet has the highest frequency of the visible spectrum. As you can see here, red is less frequent than violet, right? You see it, So it has less, in the same amount of times, you have less bumps produced as opposed to violet. So red is less, has a lower frequency than violet. The frequency of a sound wave determines its pitch. A bass note has a low frequency and a treble note has a high frequency. Speed. This is the rate at which wave fronts of a wave propagate, and it depends on the medium of the propagation. At a boundary between media, the speed changes and the wave undergoes refraction. When a wave refracts, it bends. We did a video on refraction where we saw light leaving air and entering glass, and it bends as it goes through the glass. It also, via calculation and experimental observation, the light actually slows down. So comparing the behavior of light and sound. Light has a speed of 3 × 10⁸ meters per second in a vacuum. Sound has a speed of 330 meters per second in air at 0 degrees Celsius. Light can travel through a vacuum, whereas sound cannot. Speed of light travels greater in a media of lesser density. For example, light travels slower in water or glass. And just look around for the video, it's there somewhere, so look for it, you'll see. The speed of sound is greatest through solids, less in liquids, and least in gases. Please note, the speed of sound is greater through gases of lesser density. Molecules of lesser mass respond more readily to vibrations than those of greater mass. Sound therefore travels faster through air than through carbon dioxide. Sounds travel faster in solids because of the closer packing of the particles and the rigidity of the bonds in a solid, which allows vibrations to transfer more readily. Sound also travels faster through gases at higher temperatures because the increased kinetic energy allows vibrations to be passed on more readily. So let's look at this. We have the speed of sound in steel, and the speed of sound in water, and of sound in air. So 3 different media. What are the units of speed? Correct, meters per second. In which medium does sound travel the fastest? Correct, steel. Why does sound travel the fastest as per your answer given above? Yes, because steel is the densest of the 3, so you have more rigidity, more atoms, and therefore more vibrations happening. And so because sound needs matter to travel, steel is the perfect device for it to travel through. Now, the speed of a water wave is greater across a deeper region. Right? When you see surfers, they're actually looking for the greatest wave, and they actually go out. They go out into the ocean. They don't get high waves in the shore. A wave front is a line perpendicular to the propagation of a wave on which all points are in phase. Wave fronts are generally taken through crests of transverse waves and through compressions of longitudinal waves. Points in a progressive wave are in phase if the distance between them along the direction of propagation is equal to a whole number of wavelengths. When points are in phase in a progressive phase, they have the same displacement, direction, and speed in their vibrations. Looking at the graph, points A and F are in phase, and so are points E and J. What other points are in phase? Correct. B and G. What else? F and K. Correct. Any more? C and H. Yes. D and I. Correct. Which points are out of phase? A and B, F and G, K and L. Yes. The speed of a wave may be determined using the following equation. Speed equals to lambda times frequency, where V means speed, H, the lambda means wavelength of a wave in meters, and F means frequency of a wave in 1 per second, so per second. Likewise, wavelength is equal to speed divided by frequency, and frequency is equal to speed divided by lambda. The speed of a wave may also be determined using the following equation, where you have lambda divided by period. Since F is equal to 1 over T, where T means period of a wave in seconds, likewise T will be equal to lambda divided by speed, or lambda is equal to velocity times period. Now all of this, you're only going to know it or get a customer acquainted to it once you start doing questions. The general wave equation. So the general wave equation incorporates all of these, right? And so you would usually see it looking something like this. It's not going to look like, you see how I have it here? It's easier to remember like this. All of them are related. Okay? So where N represents the refractive index of a medium, theta 1 represents the angle of incidence, while theta 2 represents the angle of refraction. Okay? When a wave moves into a new medium, its speed, wavelength, and sine theta also doubles. However, the actual theta will not double, but it will get bigger, right? So it's just the sine theta that will double once sine is attached to it, but the actual angle will not double. If the speed of the wave doubles, then its wavelength will double, and so will the sine theta. That will double. The period and frequency of the wave does not change when a wave passes from one medium to the next. Again, the period and the frequency of the wave does not change when a wave passes from one medium to the next. Its speed does, right? Slows down. See you around for part 2 of waves, sound, and light.